There are three free body diagrams we can choose to draw in the situation. Whether or not they will all be helpful, um, we don't know. Well, I mean, you might know, but we can always just draw them anyway, and maybe they'll be helpful. So we can draw a free body diagram for each bucket, but then we can also draw the free body diagram for the entire system if we treat both buckets together as a 3 kilogram mass, 2 plus 1. Then as a system, the 3 kilograms has 40 newtons force upwards, which I'll just label as tension. And it has gravitational force downwards, which, like, should I draw this longer, shorter, or the same size? Well, I can calculate it actually. So m times g, 3 times 9.8 it's less than 40. So I will draw this a little bit shorter. So the system free body diagram could turn out to be useful. And then we can draw the individual free body diagrams as well. So I'll just distinguish them by writing the masses in them. So we have a 2 kilogram bucket we can draw the free body diagram for. And we have a 1 kilogram bucket we can draw the free body diagram for. The 1 kilogram bucket's going to be the easier one. It's got its own gravity. And it's got its tension, rope 2. So actually maybe I better use some subscripts here. I'll use T1 to represent the upper rope and T2 to represent the lower rope. As I kind of figured out as I was thinking about the numbers for the system diagram, this thing's going to accelerate upwards. This 40 newtons is larger than the total force of gravity. So this small bucket by itself also needs to accelerate upwards. The buckets are going to be moving together here. So this T2 that I just drew, it is larger than the force of gravity of the 1 kilogram bucket. Now, the 2 kilogram bucket is the most complicated one because it's got 2 ropes attached to it. It's got a upwards rope attached to it, which is T1. It's got the downwards rope attached to it, which is T2. But it's also got its own gravity. So now it's just getting messy here. But those would be the free body diagrams that you have at your disposal to work with. I'm actually going to add a few more subscripts here. The FG, that's a force of gravity, but it's different for each free body diagram. For the 1 kilogram bucket, the gravity is going to be less. So I'll use a subscript of 1, a subscript of 2, and a subscript of 3. Is that a good idea? I'm just going to go with it, see where that takes us. Okay, so I'm going to start trying to answer these questions here. So part A. Determine the acceleration of the buckets, plural, both buckets. So I think the best free body diagram to choose for this situation would be the system free body diagram, because I know the numbers for that. I know the 40 newtons is applied to the whole system. And I know the mass of the whole system, which lets me calculate the gravity of the whole system. So I have all those numbers. So I'm going to use that to calculate the acceleration. So F net for the system will be the top tension. I'll use magnitudes here. The top tension subtract the gravity of 3 kilograms. I knew, remember, I'm going to write this down just. I know that 40 is bigger than the total gravity. That's important. You have to actually figure that out first before I could write the equation that I just wrote. I can only write the equation I wrote because I knew that the tension was bigger. And I knew that because just calculate this here. 3 times 9.8 is 29.7. So that is correct. All right. So I will change the F net to MA. And the gravity to mg. Now remember, this m is it's 3 kilograms for the whole system. And then I will isolate. And substitute. Okay, I am doing the wrong thing here. I am supposed to find the acceleration, so I isolated for the wrong thing. Okay, isolate for acceleration. Substitute 40 newtons minus 29.7. I have that calculated at the bottom there. Divided by the mass. We're using 3 kilograms here. Okay, get out my calculator. So I'm getting 3.43. That's going to be the 2 sig figs. We'll keep a couple extra though because I'll be needing it for part B. All right, so it's 3.4 meters per second squared. The direction is going to be up, so I can add a final statement here. Okay, part B. Determine the tension of the rope connecting the buckets. So basically find FT2. So look at all my free body diagrams. I'm going to choose one that's got FT2 in it. And that's going to be one of the individual buckets free body diagrams. And I'm going to choose the simpler one, which would be the 1 kilogram bucket. That one only has 2 arrows in it. Okay, so use the free body diagram of the 1 kilogram bucket. So that bucket is showing me that my net force is going to be FT2 minus FG. Now, this FG is different than the FG in part A. This is just the 1 kilograms worth of mass. Okay, so this time I will isolate for tension. So F net plus FG1 equals tension. Replace the F net and the gravity with its formulas. So MA plus mg, and this is a 1 kilogram bucket. So it's basically 1 times acceleration plus 1 times 9.8. The 1's not going to really do anything, just mathematically. That's a nice number. I'll write it in anyway. Get my calculator out. I'm coming up with to 1 decimal place, because we're adding, we go with decimal places. I got 13.2 newtons. So that's how strongly the second rope is. And that's the end of the question, but I'm going to do a little quick check here, actually. I'm going to use my middle free body diagram to do a little bit of a check. So if the top tension is 40 newtons, and if the bottom tension is correct, it's 13.2 newtons, the gravity on the 2 kilogram bucket would be 2 times 9.8. That would be 19.6 newtons. So if everything was done correctly, the net force would be 40 minus 13.2 minus 19.6, which equals to 7.2. And if we do the acceleration equals net force over the mass, 7.2 over the 2 kilogram mass gives me 3.6 meters per second squared, which is I'm not that happy with that, because acceleration is supposed to be 3.4, but it's 3.43 repeated, so it's actually slightly more than 3.4, which may have threw some other things off. But it's all supposed to match up. So I think, yeah, maybe the rounding maybe threw it off to my disliking, but I think the math is right here. Okay, actually I found the big culprit. The big culprit is this. It's actually 29.4. 3 times 9.8 is 29.4. So that messed some things up. But I'm not going to redo this video. Just that mistake carried through this whole thing, but the steps are still accurate.